Alright, hey guys, what's going on? So today we're going to be talking about quantum mechanics and starting to bring the language of quantum mechanics into string theory because inevitably we have to do this, right? String theory is an attempt to unify quantum with classical or general relativity more broadly. And so we're going to review quantum mechanics, but we're also going to dive into the concept of compactified coordinates and how we can add more dimensions to our space without really changing the structure of the space. So let's go ahead and get started. Make sure to hit that like and subscribe button. Now you can become a member also on YouTube. You can become a member on Patreon as well. Let's go ahead and get started. All right, so we're talking about quantum mechanics for string theory today, and towards the end of this video, we're going to talk about how we can get compactified quantum dimensions, if you will. We're not going to really talk about Claviau manifolds or anything like that. We're just going to merely introduce the topic, and it'll come back up later. So we've covered a review on special relativity and light cone coordinates, and now we're going to move to a review of quantum mechanics. Move my mic a little bit before we dive into string theory. So in quantum mechanics, we need to understand that the quintessential idea of the particle in a box, right? So if you haven't seen my playlist on physical chemistry, I went through a detailed derivation on all the necessary equations for your quintessential, the sort of go-to that all students have to understand, the idea of this quantum particle in a box. Okay. And so we're going to go through this again because I want these playlists to be relatively self-contained, but I'm also going to be referencing those playlists, other playlists that I'm making. So, and as for the physical chemistry, I'm continuing on that. I realize I've slacked a little bit. Things have been a little bit busy on my end, but all right, so let's go ahead and get started on this. So we're going to start with our wave equation. So I haven't derived this wave equation, right? You can derive this thing, but this is going to be mere the starting point here because I don't want to go too far back. So I'm sort of supposing that you know what the wave equation is, how you can derive it, and so forth. So we can express the solution to this wave equation in the following way. So we have our total solution U, which is here and here. It has a spatial part, and we're going to say it has a temporal part, and the temporal part is going to take this form right here of cosine omega t. So if we plug equation 2, this guy, into this guy, we're going to get this here, where omega is the frequency along the temporal domain, or along the temporal component, t. And so when we take this derivative, or when we take the time derivative, we get this omega squared out, and then we get this 1 over v squared. And then we're going to get, for our spatial part, derivatives of the spatial part, right? So if we're just looking at just x and not y and z dimensions, this is where we get this bit right here, right? So really, this is just literally we just put u into here, and so we're putting this in for u. Spatial derivative, we get this. Temporal derivative, we get 2 of these, and so we get this here, and then from here to here, then we redefine some variables. Omega is 2 pi times the frequency, and so we get this right here. All right, we can calculate the wavelength of the particle by considering that the total sum of the particle's energy is given by this thing, right? So this is kinetic energy, right? The reason this is kinetic energy, if you're not familiar, we get this from our 1/2 mv squared, right? If momentum and p equals mass times velocity, so we could see p squared is m squared v squared, and so then we divide by m. If we divide by m, we just get mv squared, right? So we have this part. This app sometimes does not want to cooperate. But you could see then, just by knowing this and this, then we can get this part. And then this is the function for our potential energy. We don't know what the potential energy is, so we're going to keep it at an arbitrary function for right now. And then later we'll just completely get rid of it when we consider a free particle. So from here to here, then we get this, right? We want to isolate P, and so to isolate P, we get this thing, and then we can reintroduce the idea this is our de Broglie wavelength, right? Is h over P, where h again is Planck's constant, and we get this over this. And so when we take equation 3, then, so equation 3, this guy, and we plug it into this guy here, right? Or really what we're doing is we're saying we take this here, and it shows up right here, right? So we're going to put this in for lambda, okay? And what we end up getting is this right here. And you can pause the video if you want to see how that works. But it's just a bunch of algebraic manipulations. And so from here then, we get this. And this is the famous Schrödinger equation. So the Schrödinger equation really just is this idea of, well, it's the wave equation, right? We kind of just proposed this solution here, and by proposing the solution to our wave equation, we naturally get our Schrödinger equation. And when we set our this guy equal to 0, we're going to see that we're going to get the Schrödinger equation for a particle that's free, in which there's no interactions taking place. So again, this is the famous Schrödinger equation. We can write it like this, and this is particularly useful because now we can see that this thing is an operator. It has some derivative plus some function. This thing's going to operate on psi, and it should give us psi back, just scaled by some number. And so what's this say? Well, this says that psi can't be some just arbitrary function, right? It has to actually fit such that when you take two derivatives of it, two spatial derivatives of it, and you do all this stuff, right? You add your v, and you also multiply by this. The effect is going to have to be just a scaled version of that function by E, and the scale is the energy, okay? That's associated with this operator. So this thing is not an arbitrary function, right? It can't be arbitrary, right? This not arbitrary by virtue of this eigenvalue equation. This is an eigenvalue equation, right? Because E is the eigenvalue of this operator right here. All right. So we can identify the operator H then as follows. So H is going to be all of this stuff in here, all right? And H then, so it's an operator, and its associated eigenvalue is E, which is the energy. And right here we have H is equal to all of this. Okay. So this has become an eigenvalue problem because operators such as matrices have eigenvalues. And in quantum mechanics, these eigenvalues are associated with observables of the system. So energy, for example, is an observable of our system when we consider this H, or this operator right here, okay? In our system, so far, the eigenvalue of the H operator is the total energy of the particle. Okay, and we can visualize operators as operating on some arbitrary function to give us an observable. So we have some function, again, not really arbitrary, right? This isn't arbitrary. It's arbitrary to a degree insofar that it has to fit, it has to obey this differential equation. But you take some function, you have some function, operate it on it with H, and then when you do that operation, you should get an energy associated with that operation. The energy, again, is just a scaled version of this function, or is the scale by which you are scaling this function up or down. All right. So we can identify a kinetic energy operator then from equation 4, right? So this is our Schrödinger equation again. Excuse me. We have our kinetic energy operator is this thing, right? So that's this bit right here. It's our kinetic energy part, and this is our potential energy part. And when we do that, if we note that the kinetic energy is momentum over 2m, well, then we could say that the momentum operator then is this, right? Because if we take this bit right here, well, that's the momentum part. That's the momentum squared. All right. And then over 2m, well, I'll do over 2m, well, that's this guy right here. Right, so we can then identify this momentum operator as being the green part. So I'll just do that in green. So this is the momentum operator. All right. And so we can see that this is squared. Everything in here is squared, so we say that the momentum not squared are these two guys. So this here is our momentum operator in our x direction at p hat, right? So, okay, so we have now a momentum operator. So let's keep this in mind as we go forward. So now we're going to take equation 5. So why I labeled the equations, this guy right here. And we're going to set the potential energy equal to 0. This is in concordance with calling this particle a free particle. Again, when V is equal to 0. So this is the same thing as equation 5, right? Or did I label both of those 5? Oh, I did. They're kind of they're the same equation, right? This here is H. We're going to set this thing equal to 0. So when we do that, we just have this then. So we have no V in this equation now. No V of X. And we're left with just, this is all just some number. And then this is the operation on psi. Okay, notice now there's no time dependence in this operation, right? This is just spatial. So the boundary conditions that we're going to impose on this wave function are this, and this is critical. When we suppose these boundary conditions, this is where we're going to get the idea of quantum, right? Because and here's the following. This is why, right? So we're going to get, when we do this, we can realize that the solution to this equation is just sinusoidal, right? This is just a constant. This here is double derivative. Well, the double derivative of this thing, right, is going to be 0. And you could plug this in, right? You could plug this into here and see that that is indeed the case. And so you could pause the video if you want. I'm not going to do that right now. This is just, again, a lot of this is review. So the general solution for this equation is this guy where k is equal to all this stuff in here. So that's all this stuff. Okay. All right. So given boundary conditions, then we can say therefore that. So when we look at our boundary conditions, this is psi at 0 and psi at A. Psi at A is going to be equal to 0. So that means we can sort of kick out this cosine bit, right? Because the cosine part doesn't obey it doesn't obey this satisfaction here, or this boundary condition, right? Because cosine is at 0 going to be 1, and at A going to be 1 as well, so not 0. So we want sine of 0 and A is going to be 0 though. So we keep the sine part, which is right here. We're going to ignore the trivial case where B equals 0, and we could see that for this boundary conditions then, we need Ka to be equal to some factor of pi, right? Because sine of something pi is going to give us 0. So Ka has to equal n pi, where n goes from 1 to 3. And this is the quantum part, right? Because now we're seeing that there's only particular solutions where n is equal to 1, 2, 3, 4. It's not a continuum, it's quantum. Okay? From equation 10 then, so we take equation 10 right here, we can conclude that the energy then is this guy right here. And the way we get that, again, is we have our energy, and we said K was equal to n pi, so taking all of that, we get this, where H, sometimes you'll see this with an H bar instead, and so you should get a 2 right here instead, right? So depends on how, if you like Planck's constant or not. But this is how this is then our energy solution. our values for our energy, right? So at the first energy level, n is going to equal 1. At the second energy level, n is going to equal 2, and so forth. We can see that the energy now is quantized, and this all really fundamentally came about by imposing these conditions. Everything else was just wave. This is just a simple wave equation. Nothing about it was really quantum until we said, okay, we want our boundary conditions to look like this, and right immediately when we did that, we can see that things are getting quantum now. So the solution, therefore, is this thing right here. Now we're going to stop here. We're going to take a look at these solutions, and then we're going to move on to how this is going to be relevant to string theory. We're going to talk about compactifying dimensions and all this stuff. So we can visualize the solutions in this way, right? So psi 1, so psi where n equals 1 is going to look like this. When we square it, it's going to look like this. So when we square this guy, it's going to look like this. The reason we square it is because we want all of our values to be positive, right? Because we can't have negative probabilities. Negative probabilities don't make sense. And so really what we're looking at are solutions in this column right here. So these are the sort of the raw solutions, right? These are the things that look like this, but then squaring again, the squaring is a solution to our wave equation. And so we get these guys here, right? And so we have points where there's no probability, right? And so that's interesting, right? That's a consequence of going quantum. And then we have all the energy levels, right? So we have this one, and this guy right here. All right. So now let's start adding extra dimensions to this, and we're not going to add extra dimensions in the sense that we did in my physical chemistry playlist. We're going to add periodic dimensions, okay? And this is where string theory is going to start edging itself into our narrative. So suppose now I'm going to erase this. I'm going to tell this story all over again. I filmed this once already, but the film didn't work, and so let's start over. So the idea here is that suppose you're walking in some x dimension, all right? So here you are, you're walking along this x dimension. You're at position 0, and then you're at position A, okay? Then you go to position A. So you're walking in this direction. Suppose you see a tree right here, okay? You see a tree. All right. You see this tree, and then you walk some distance, and then you see the tree again. I'm not drawing it to, and this tree looks exactly the same. And maybe to make this a little bit more realistic, say you have a rock right here and a rock right here, and you have a rock right here and a rock right here. So the situation looks exactly the same. The concept here is periodicity, right? So periodicity. This is where things get weird, because you think to yourself, I just saw that tree. That tree looks so familiar to me. I'm pretty sure I went in a straight line. So you could sort of intuitively think to yourself, well, okay, maybe I didn't. Maybe I actually walked in a circle. Okay? By virtue of walking in a circle, then what you're doing is you're saying you identify point 0 with point A. Okay? They're the same exact point because you're making this observation that the tree is the exact same tree. Okay? And so what I'm going to call a periodicity, or a periodic, or a periodic dimension. And with this in mind now, so I have this image, right? So I have this image where we identify points with each other. Okay, so if you're walking along this line here, you identify this point as being the exact same as this point. Okay, that's the same thing here. So these points are the same point. With this in mind, our boundary conditions now are going to be a little bit weird. So the boundary condition is going to be different in this case, right? So you could say, well, you traveled along X, right? You traveled in this direction. Okay, that we could say that that's the X direction from 0 to A. And these are all linearly independent, right? So this thing is linearly independent from Y, and the reason for that again is because this thing right here, when we consider all three dimensions, that's going to be d squared dx plus d squared dy squared plus d dz squared. And so each one of these is going to have its own independent solutions that look like this, right? So you're going to have psi of n of x, y, and z all equaling b, actually, no. Our solution is equal to psi, how do I want to write this? It's going to be equal to, here, actually, let's go back to this equation over here. The point I'm trying to make, and we're not doing a very good job at it, the point I'm trying to make is that our solution, I guess I don't have it here, but our solution, the solution along each independent axis, it's this guy right here. It's this guy right here. This thing right here. This thing is going to be, we're going to have a psi of x. We're going to also have a psi of y and a psi of z, and those things are linearly independent from one another. Okay, I'm sort of getting a little bit astray here, and I don't really want to. So the point. Okay, so the point again is that we have these linearly independent dimensions. Okay, in some of these dimensions, we have imposed boundary conditions that look like this. Okay, these are the boundary conditions we've dealt with so far. This boundary condition looks a little bit different. If you look at this, we're saying that psi of y is equal to psi of y plus 2 pi r, right? This is the circumference of a circle. We're saying that those 2 points are equal to each other. They're not zero, they're equal to each other. Okay? And that's a big thing here, right? We're saying that for our boundary conditions in the x dimension is this. We're now going to say we have a y dimension, but it's a weird y dimension, right? It's not. We can have a y dimension that has these boundary conditions, but we're going to say we have a y dimension now that has these boundary conditions. We can have this plus another psi of. We could have something like this, right? We have x and then psi of y of 0, psi of a, y of a equals 0 as well. We can have these two guys and still have this guy here. This is a completely, the naming scheme is just a little bit confusing because, and this is what Barton Zweibach does in his book. I don't like it, but that's all we got, right? It's what we're dealing with. And so I could literally name this something else. I could name this, I could have some weird symbol in here. We would just have to change that symbol right there. The idea again is that we have linearly independent dimensions, okay, that obey this type of boundary condition, but then we have another set of linearly independent directions that obey this solution. or that obey this boundary condition, okay? So this boundary condition for our y direction is our solution is that it's different. So the solution is going to be different, right? Because here are our boundary conditions. Our solution for our y dimension is therefore going to be different because of these boundary conditions, right? The idea here is that, well, we came up with this solution for this boundary condition. This is the solution for this boundary condition. You can sort of easily kind of see this, right? Because if we have, here, I think I already wrote it down here. If we could take note that L equals 0, when L equals 0, we get this right here, right? So when L equals 0, so L is the quantized, this function is quantized, right? When L equals 0, we just get this B1 right here, okay? And then this here is going to be, this bit's going to go to 0, right? Because sine of 0 is just going to be 0. Okay, so if L is 0, we get this right here. This is going to correspond to a low energy solution, which means that low energies that are low energies in our physics our solution doesn't change very much, right? So the solution is just this constant. Similar to how we derive the energy eigenstate for our one-dimensional particle in a box, we can see that the solution for our two-dimensional system now is this thing, where this bit right here matches exactly right here, okay, with h bar instead. But then we have this bit, and this bit came from introducing this new boundary condition for this new variable. That's essentially what we're doing. We're defining a new independent variable that has different boundary conditions, okay? And so when we do that, we get this extra piece right here, okay? We can also see that when this is 2 pi, right? So if we have 2 pi in here, we can see that psi of L, the structure of this is going to be the same if we have y plus. If our argument in here is y, right? Then and the argument in here is y, it's going to be the same as the argument in here is y plus 2 pi r, y plus 2 pi r. All right. So again, I can't stress this enough. The idea is that, I'll say this one more time, the idea here is that we have two different types of independent variables now. Okay, it's not two different independent variables, it's two different types. Okay, I want to stress that a lot. One type is our normal, what we're used to, right? That's this type right here, without any periodicity, right? We just have this situation right here. But then the other type has periodicity to it, this idea that I've talked about in this situation. Okay, this is that periodicity, and what satisfies our solution for this periodicity for our wave equation is this right here. Okay, so it's not that these two are zero. These two again are zero because we're saying they're zero, but these two are not because this is just periodic. Okay, it's a periodic boundary condition. All right, I hope I made that clear. Maybe I didn't. If I didn't, please put comments below. But we can see that when R in this equation is much less than A, the low-lying energy doesn't change, and the energy gets large. So this bit doesn't change if R is much greater than A, right? Because if it's much greater than A, this thing's going to blow up. Or no, this thing's going to get really small, and then that square's going to be even smaller. So when this is really where we're going to start talking about strings, right? Because when R is really small, you can imagine a really, really tiny circle. But it has the circle, the radius of that circle has to be much smaller than this distance here, right? Because this is what A is, right? It's the distance. Right, so Okay, this is getting a little bit weird, but let's keep on going. So if R is very small, we can get our regular quantum mechanical energy levels. So in some sense, this is a more general energy solution with some energy levels being hidden from us by extra periodic dimensions. When L is 0, however, we recover equation 13. And equation 13, that's what I just said right here, right? So when this bit is 0, this whole thing goes to 0, and we just get equation 13. So we can ask what happens then. What happens when L equals 1? This is going to correspond to a ground state, but not a ground state in this periodic condition, in this periodic boundary condition. This is going to be a ground state in our, sorry, I said periodic. This is the ground, psi 1 is the ground state for this non-periodic dimension, when L equals 1 is the ground state for the periodic dimension. Okay, so this is ground state for periodic dimension. All right, so what is that, right? So if we put 1 in here, well, this approximately, so K is 1, L is 1. This approximately is going to equal this right here. Because when we say R is much less than A, then we can approximate this and we can say, well, it's about this right here. Because if R is much less than A, this thing's going to get really small, right? And so so that's where we get this bit right here. Okay. So we can compare this then. We compare this ground hidden state, or a ground state for our periodic dimension, with the ground state in the non-periodic dimension. So the ground state in the non-periodic dimension, we're going to have an energy that looks like this, or not really an energy. Wait, so this is going to be this bit right here, right? So we have K, which is all these constants, okay? And we have pi over A. So K, pi over A. And then our ground state for our, when we include our periodic dimension, is going to be approximately 1 by 1 over R squared. And so we can compare this K pi over A to 1 over R. And so we get that K is approximately equal to 1 over pi times A over R. And when R, again, is really small compared to A, we could see that when this thing gets really small, our denominator is getting really small, so that means the overall number is going to get really big. Okay, and this corresponds to a very, very large energy. So the smaller this periodic dimension is, the more difficult it is to probe. And this is what we want to keep in mind when we start talking about strings. We start talking about high energy. So this is really high energy solutions. High energy solutions have this notion of periodic dimensions to them, okay? I want to take maybe 1 or 2 minutes to just briefly talk about if this is even worth it, right? There's all this hullabaloo in the string theory community on whether or not string theory is actually a relevant theory for physics, okay? People like Edward Witten say it is. People like Brett Weinstein or Eric Weinstein say it's not. When we propose these new set of boundary conditions, we can get solutions to our differential equation. But does a solution to our differential equation necessarily mean that it's real? Well, that's sort of a question for the philosophy of mathematics and physics. Do all solutions to all proposed or all derivable all derivable differential equations, does every single solution work? Every single solution works, but does every single solution exist in the natural world? That, again, is a question that is it's contended, right? A lot of people will debate this. So again, I kind of want you guys to sort of think of this as string theory is super interesting, has a great, very interesting mathematical structure. However, at the heart of this, we have a solution to a differential equation, really just our wave equation, our Schrödinger equation. It's a solution, but it's really, really high in energy. And does this really, really exist? A compact, periodic, high energy dimension. And we can do this for any number of dimensions, right? Because I said up here, we can put any symbol in here. It's just going to represent a different axis, right? We're going to, instead of X, Y, and Z axis, we can have 26 different axes. Okay. Again, is this something that we really want to entertain? And so I'll leave you guys at that question, and I'll see you guys in the next video.